Welcome! In this lesson, we will explore the fascinating world of dynamic simulation, which is a cornerstone of understanding how systems change over time in many fields of science and engineering. Our primary goal today is to learn how to simulate the motion of particles using what are known as kinematic equations. These equations describe movement in terms of position, velocity, and acceleration, without necessarily delving into the forces causing that motion. For instance, under constant acceleration, the velocity at a given time t is the initial velocity plus acceleration multiplied by time, and the position at time t is the initial position plus initial velocity times time plus 1/2 times acceleration times time squared. We will learn to apply these equations through discrete time step updates, which is an efficient way to predict a particle's trajectory. This approach is powerful because it allows us to visualize and analyze motion even if the underlying forces are complex or unknown. We will begin with simple, one-dimensional scenarios and gradually build our understanding. It is also worth noting that simulations explicitly incorporating forces will be covered in a subsequent lesson. But for now, our focus is purely on the kinematics of motion. Instead of immediately tackling motion with acceleration, we will begin with the simplest possible case: a single particle moving with zero acceleration. This means the particle travels at a constant velocity along the x-axis. It starts from an initial position, let us call it x0, and moves for a specific duration. Throughout this simulation, its Glaby coordinate will remain fixed at 0. The kinematic equations governing this simplified motion are: the x position at any time t is equal to the initial x position plus the initial x velocity multiplied by t, and the y position at time t is always 0. This scenario serves as a fundamental building block, allowing us to establish our simulation techniques before moving on to more complex situations involving acceleration. The code block you see implements this simple one-dimensional constant velocity motion. It starts by importing necessary Python libraries for random number generation, numerical operations with NumPy, plotting with Matplotlib, and dynamic display capabilities from ipython.display. The code then defines the size of our simulation box and sets a maximum speed for the particle. To make each simulation run a bit different, the particle's initial position and velocity are chosen randomly within defined limits. The total duration of the simulation is then calculated. Two key functions are defined: one to calculate the particle's x position at any time t, and another for its ed position, which consistently returns 0. The core of the animation is a loop that iterates through discrete time steps. In each step, the display is cleared, the particle's new position is calculated, and then Matplotlib is used to draw the particle as a red dot, its starting point as an orange x, the origin as a blue x, and the x-axis as a dashed line. A display function updates the visual, creating the illusion of movement. Now here is an exercise for you to try. Building upon the previous example of a single particle, your task is to modify the code to simulate the motion of n particles, where n can be any arbitrary positive integer. Each of these n particles should have its own unique initial x position, which we can denote as p sub I, and its own initial x velocity v sub I, where I represents the index of each particle from 1 to n. Think about how you would need to store the initial positions and velocities for multiple particles, perhaps using lists or NumPy arrays. Consider how the update loop would change to calculate and plot the position of each of the n particles in every time step. This exercise will help you generalize the concepts we have discussed and is a great step towards simulating more complex systems with multiple interacting objects. Next, we will move on to simulating a classic two-dimensional system: the simple pendulum. Our approach will again be based on a kinematic equation, this time describing how the angle of the pendulum, theta, varies with time. To do this effectively, we first need to understand the relationship between the pendulum's period of oscillation, t, and its physical parameters, which are its length L, and the acceleration due to gravity g. The angular frequency, omega, is given by omega squared equals g divided by L, and the period t is then 2 pi divided by omega. The total duration of our simulation and the size of the simulation box will be expressed in terms of these characteristic scales: t for time, and L along with L times the initial angular displacement theta 0 for spatial dimensions. The kinematic equation governing the oscillatory motion, assuming small angles, is that theta at time t equals theta 0 times the sine of the quantity omega times t plus phi, where theta 0 is the maximum angular amplitude and phi is the initial phase. This equation is the solution to the differential equation for simple harmonic motion. To simulate the pendulum's movement in 2 dimensions, we need its instantaneous x and y positions. These are related to the angle theta and the length L through simple geometry. If we define the origin at the pendulum's equilibrium position, then x at time t is L times sine of theta at time t, and y at time t is L minus L times cosine of theta at time t. The accompanying diagram visually represents this coordinate system. The following code demonstrates how to simulate the simple pendulum's oscillation using the IPython display method, which is similar to what we used for the first particle animation. For this specific simulation, we assume an initial condition where the pendulum starts its swing from the equilibrium position, meaning the angle theta at time t equals 0 is 0. This corresponds to setting the phase angle phi to 0 in our kinematic equation. The code begins by importing the necessary libraries and initializing key parameters like the initial angular displacement theta 0, which is converted from degrees to radians, the length L of the pendulum, and the acceleration due to gravity g. From these, the angular frequency omega and the period t are calculated. Next, 2 functions, x of t and y of t, are defined to compute the pendulum bob's coordinates. These functions use the angle theta, which itself is determined by theta 0 times sine of omega times t. The x-coordinate is L times sine of theta, and the y-coordinate is L times the quantity 1 minus cosine of theta, reflecting our chosen origin. A time array is generated for the simulation, and the plot dimensions are set. The animation itself happens in a loop that iterates through each time step. In every iteration, the output from the previous frame is cleared. Then, the code plots several elements: the fixed pivotal point as a blue X, the entire trajectory the pendulum will trace as a series of red dots, a line representing the pendulum rod connecting the pivot to the bob, and the bob itself as a circle at its current instantaneous position. Reference x and y axes are also drawn. The display lime function, along with clear underscore output, creates the animation, and setting the aspect ratio to equal ensures the pendulum's motion appears physically realistic. Let us now shift our focus to another common physics problem: 2-dimensional projectile motion. We will simulate the path of a projectile using its kinematic equations, which describe how its x and y coordinates evolve over time under the influence of gravity. The vertical position, y at time t, is given by the initial y position plus the initial y velocity times t minus 1/2 times g times t squared, where g is the acceleration due to gravity. The horizontal position, x at time t, is the initial x position plus the initial x velocity times t, assuming no air resistance. To effectively set up our simulation, it is crucial to understand the characteristic scales of the motion. These include the half-time of flight, often denoted t sub 1/2, which is calculated as the initial speed v0 times the sine of the launch angle theta, all divided by g. The range, r, is the total horizontal distance traveled and is given by the initial x position plus 2 times the half-time of flight multiplied by v0 times the cosine of the theta. The maximum height, h, is the initial y position plus v0 times sine of theta times the half-time of flight minus 1/2 times g times the half-time of flight squared. These quantities, t sub 1/2 for the timescale and r and h for the length scales, will guide us in determining the appropriate duration for our simulation and the dimensions of our display area. This code block implements the simulation for two-dimensional projectile motion, again utilizing the IPython display method for animation. It begins by importing the necessary Python libraries like NumPy for numerical calculations and Matplotlib for plotting. The initial conditions are then defined. Starting position x0 and y0, the acceleration due to gravity g, the initial launch speed v0, and the launch angle theta, which is converted from degrees to radians. Using these initial values, the code calculates the characteristic quantities we discussed: the half-time of flight, the range, and the maximum height. These are then used to determine the total simulation time and the boundaries for our plot. The initial x and y components of the velocity are also computed. Two functions, x of t and y of t, are defined to calculate the projectile's horizontal and vertical positions at any given time t, based on the standard kinematic equations for projectile motion. The animation occurs within a loop that iterates through time steps. In each step, the output is cleared, and a new figure is prepared. The current position of the projectile is plotted as a red circle. For context, the entire parabolic trajectory that the projectile will follow is also plotted as a dashed line. Reference x and y axes are drawn, and the plot's aspect ratio is set to equal to ensure the trajectory looks realistic. Finally, labels are added for the x and y axes, and a title is displayed that dynamically updates with the current time and the projectile's x and y coordinates, providing a clear visualization of its motion. We will now introduce a more advanced and often preferred method for creating animations in Matplotlib, called Func Animation. This tool is part of the matplotlib.animation package and allows for the creation of smoother, video-like simulations. The Func Animation function typically takes several arguments: a figure object, which will host the animation, an update function that defines what happens at each frame, a sequence of frames, often an array of time values, a blit flag which can optimize rendering, and an interval that controls the speed of the animation. The update function is central to this process. It is called for each frame and usually takes the current frame value, say, time t, as its input. A common pattern is to first create an initial plot object, for instance, sdLine from ax1.plot, which acts as a placeholder. Inside the update function, you calculate the new data for the current frame, say xDummy and uDummy, and then use the set_data method of your plot object, like sdLine dot set_data xDummy LiDummy, to refresh it. The update function must then return this modified plot object. Therefore, you, as the programmer, need to design the parametric equations, x of t and y of t, that describe how the simulated object's coordinates evolve over time. The interval parameter, specified in milliseconds, controls the delay between frames. For example, an interval of 200 means 200 milliseconds between each frame update. We will soon see an example illustrating this for one-dimensional motion. The practical note: to save or sometimes even display these animations, you might need to install a package called FFmpeg. This can usually be done using commands like conda install ffmpegs in an Anaconda terminal, or by typing %pip install ffmpeg directly in a Jupyter Notebook code cell. Let us delve a bit deeper into the practical steps of using Func Animation. The very first step is to create a Matplotlib figure object and an axis object that is attached to this figure. This is essential because Func Animation needs to know which specific figure it is supposed to animate. Then you typically create an initial plot object, such as sdLine, obtained from ax1.plot. This line, or point, is initialized with empty data and acts as a placeholder that will be dynamically updated in each frame of the animation. The magic happens with the set_datas method. For example, sdline.set_data, xdummy, ydummy, takes the newly calculated coordinates for the current time step and feeds them into this placeholder plot object. This is generally more efficient than creating an entirely new plot in every frame. The update t function, as we have discussed, is responsible for calculating these new xdummy and udummy values based on the current time t, or frame number, and then using set_data to refresh the plot. Crucially, this update function must return the updated line object, or a sequence of such objects if you are animating multiple things. The func animation command itself then takes your figure, your update function, and the sequence of frames, and repeatedly calls update for each frame, effectively stitching all these individual plots into a complete animation object, which is often assigned to a variable like Ani. To show this animation within a Jupyter notebook, you typically convert the Ani object to an HTML5 video format, and then use IPython's display.html function. If you want to save your animation as a video file, for instance, in an MP4 format, you can use the ani.save method, providing a file name like my_animation.mp4feet. Now, let us examine a specific code example that uses func animation to simulate the simple one-dimensional motion we first looked at. This will render the animation as a much smoother video compared to the frame-by-frame IPython display method. The code begins by importing the necessary Python modules, including NumPy for numerical arrays, matplotlib.pyplot for plotting, IPython.display for showing the video, and, importantly, func animation from matplotlib.animation. The x and I functions are defined to describe the particle's motion. X changes linearly with time, while y remains 0. Then, simulation parameters are initialized, such as the total time, t, an array of time steps, tar, the particle's initial position, p1, and its constant velocity, v1. These are bundled into arg1. The full range of x values is determined to set the plot limits. A figure and an axis are created, the x-axis limits are set, and a horizontal line at y equals 0 is drawn to represent the path. The line sdline equals ax1, plot, is key. It creates the plot object, a single point marker in this case, that will be animated. The update t function is then defined. For each time t, it calculates the new x and y positions of the particle and uses sdline.set_data to move the plotted point. Note that xdummy and udummy are single values, so they are wrapped in lists as set_data expects sequence-like inputs. The function returns the updated sdline object. Finally, func animation is called with the figure, the update function, the time array tar as frames, the blit option for optimization, and an interval of 200 milliseconds. The resulting animation object, Ani, is then converted to an HTML5 video for display within the notebook and is also saved as a file named 1d_uniform_motion.mp4feet. Next, we will explore a different kind of motion, the propagation of a one-dimensional pure sinusoidal wave. The profile of such a wave, which describes its displacement y as a function of both position x and time t, is given by the equation y of x, t equals a times sine of the quantity k times x minus omega times t plus phi. In this equation, a represents the amplitude of the wave, omega is its angular frequency, k is the wave number, which is related to the wavelength in units of inverse meters, and phi is the phase constant in radians. The velocity of the wave is given by omega divided by k. An interesting property is that if you reverse the sign of the wave number k, the wave will propagate in the opposite direction. For our animation, each frame will display the wave's profile, y, as a function of x, at a specific instant of time, t. The time t will evolve from an initial value of 0 to a final time, t sub last, in discrete steps. The following code will illustrate how to use Func animation to create a simulation, in the form of a video, showing this wave profile propagating along the x direction as time progresses. Let us now look at the code that animates the sinusoidal wave using Func animation. It starts by importing the necessary libraries, including ipython.display, matplotlib.pyplot, numpy, and Func animation. Then, it initializes the parameters for our wave, a for amplitude, lambda for wavelength, f for frequency, and phi for the initial phase. From these, the period t, angular frequency omega, and wave number k are calculated. Note that the sign of k is chosen here to be negative, which will determine the direction of wave propagation. An array ZAR is created, representing the range of x coordinates over which the wave will be plotted, defining the horizontal size of our animation box. Similarly, tar is an array of time steps that will define the temporal length of the animation. The vertical limits for the plot, YLO and YHI, are set based on the amplitude. The function yxt is defined to calculate the wave's displacement using the sinusoidal wave equation. As before, a figure fig 2 feet and an axis ax 2 feet are prepared, and their limits are set. An initial profile of the wave at time t equals 0 is generated, and an empty line object, SD line, is created using ax2.plot. The update2t function is the core of the animation. In each call, it sets the title of the plot to display the current time, a, and draws a horizontal line at y equals 0 for reference. It then calculates the new wave profile YAR by evaluating our yxt function for all x values in ZAR at the current time t. This new profile is then plotted by updating the data of SD line. The function returns the updated SD line. Finally, Func animation is called to create the animation object Ani2feet, which is then converted to an HTML5 video and displayed, showing the wave moving across the screen. In this lesson, we have explored how to create dynamic simulations of motion, focusing on visualizing both particle trajectories and wave propagation. We learned two primary techniques for generating these animations within a Jupyter Notebook environment. First, we use the ipython.display function in conjunction with clear_output to achieve frame-by-frame animation. We applied this method to simulate one-dimensional constant velocity particle motion, the two-dimensional oscillation of a simple pendulum, and the parabolic path of a two-dimensional projectile. The second, more advanced technique involved using matplotlib.animation.func which produces smoother, video-like outputs. We demonstrated Func animation by creating simulations for one-dimensional particle motion and the propagation of a one-dimensional sinusoidal wave. The fundamental principle underlying both approaches is the iterative calculation of a system's state, such as its position or wave profile, at discrete time steps using relevant kinematic equations. This state is then visually updated on a plot. It is important to remember that a good understanding of the underlying physics, including the kinematic equations and characteristic scales like period or range, is essential for setting up these simulations correctly. These visualization techniques are powerful tools that can help you understand and explore a wide variety of physical phenomena. And the examples we have covered provide a solid foundation for building more complex simulations in the future.